Thanks, Florian, for the introduction. So I'll talk about joint work with Kaisa Matomäki, where we study products of small primes in arithmetic progressions. So the starting point of this investigation is the conjecture of Erdős, which he made in a paper with Erdős and Sarkozy. So the conjecture of Erdős states that if you take any large prime Q, then you can represent every reduced residue class, modulo Q, as a product of exactly two primes less than Q. So in other words, if you take any A co-prime to Q, then you can always find P1, P2 less than Q, such that A is congruent to P1, P2, Q. So this we certainly expect to be true based on probabilistic grounds. So if you model the set of primes by a random set of density 1 over log Q, as in the Kneser random model, then this would be true. And so, but not much is known about this conjecture, even assuming the generalized Riemann hypotheses. So it's not proven even under GRH. Under GRH, one can get partial results. So one can show that the set of exceptional A modulo Q for which you don't have such a representation is very small, like a power of log of Q. But it doesn't quite give the full statement. And so you can think of this conjecture as a multiplicative analog of the binary Goldbach. We're looking for products of two primes that should represent everything. And so we want to study in this talk relaxations of this problem. And to formulate those relaxations, let's make the following key definition. So by EK of X, I'm going to denote the set of reduced residue classes modulo Q, such that you can find K primes less than X, whose product is congruent to A modulo Q.
So this is really K, not less than or equal to K.
Yeah, that's very important. Yeah. So that's what the E stands for, exactly K. Because if there were at most K prime factors, then one could use C theory. That would be a lot easier. Whereas here you have the parity problem at play. So that's very important indeed. So in other words, you take the set of primes less than X, and you take the K-fold product set of that set. And you want to take the modulo Q and see what residues are covered. And here in what follows, Z mod Q star is always the multiplicative group of the reduced residue classes modulo Q. Okay, and the fundamental question is, for which values of K and X can we show that EK of X covers everything? So products of K primes less than X cover all the residue classes modulo Q. Okay, so one can already ask this for K equals 1. So that's for the primes. And in that case, we have the famous Linux theorem, which states that there's a constant L such that E1Q dot L covers everything. So in any residue class modulo Q, there's a prime less than Q dot L. And over the years, there's been a lot of work on this problem. The best value of the exponent L is L equals 5 by auxiliaries, improving slightly on Heath Brown's L equals 5.5.
In this problem, there's no reason to make Q prime. You could make Q.
Yeah, absolutely. Yeah,
And in
yeah.
your
This would
problem,
be for all Q. Yeah, that's very, very true.
And in your problem?
Okay, so in our results, Q is going to be cube free. I'll explain in a moment why, but yeah. Yeah, but in Erdős conjecture, Q was prime. But it should be true for arbitrary Q. Okay, so this is what we know about E1. And so Erdős conjecture can be reformulated as saying that E2 of Q covers everything. And so conjecturally, E1 Q dot 1 plus epsilon should cover everything based on the Kneser random model. So if you have the primes of the Q dot 1 plus epsilon, they should already be enough to cover every residue class with low Q. But this we certainly don't know, even under GRH.
So is it expected that E2 of Q to the 1/2 plus epsilon?
Yeah, that also should be true. Yeah. Yeah, we just need more than q primes, a bit more than q primes, so that there's a chance of them covering everything. And then by probabilistic arguments, you expect that indeed they cover all the residue classes. Okay, so these are some conjectural results. What about unconditional results? It's not even that easy to show that ek of q covers everything for some q, for some k. So the first person to show this was Elliot Walker. So he showed that E20Q covers everything. Actually, he had two works on this. The first one had E48, and then he reduced it to E20. Okay, so we know that 20 primes, first of 20 primes cover everything up to Q. Then 3 years ago, Alexis Fuhrman, Sasha Mantarel, and myself proved that E3 of Q covers everything for all but boundedly many primes in any superdyadic interval from capital Q to capital Q squared. So in any such superdyadic interval, there's at most, let's say, 1 million exceptional Q. So it's an almost all result. And then very recently, in the past year, in fact, in the past few months, there's been some more progress. So Zabo and independently Zhao showed that E6 of Q covers everything. And Zabo also showed that E3 Q to the 6/5 plus epsilon covers everything for large enough primes. And this improved on another work from this year of Balsa Barani and Ramare and Surastad. Okay, so these are some of the previous results, and our result, the main result that I want to tell you about, improves on these by showing that E3 of Q is everything. So this can be seen as a ternary version of the Erdős conjecture. And in fact, our method can do a little bit more. So we can show that E3 Q to the 1 minus eta covers everything for some small eta, which we didn't compute explicitly, but something like 1/100 should certainly work. Okay, so in the main part of this talk, I want to give you a sketch of how we proved this result. But before we go to the actual proof, there's sort of two natural approaches one could take to this problem. One of them is not going to work, and the other one is going to work. But I'll start with the one which is not going to work, because that's also instructive to see what goes wrong there. So perhaps the most natural approach is to directly apply Fourier analysis to this problem and see what it tells us. So this would be in analogy with the standard proof of ternary Goldbach for large numbers. Okay, so we are counting products of 3 primes less than Q that are congruent to A modulo Q. So we could just expand out the indicator of the progression into its observable characters to get a sum of character sums of the primes. And we want to separate the principal character from the sum, because that should give us the main term. So the contribution of the principal character is exactly phi q squared. And all the other characters we treat as error term. So we just put absolute values around it. And we're looking at the cubic moment of the exponential sum of the primes. Sorry, the character sum of the primes. Okay. Now, if we knew that there's some cancellation in the character sum of the primes after Q, then we could easily conclude we could just apply the pointwise bound on one of the 3 copies of the character sum and Parseval, so orthogonality, on the other 2. And that would give us exactly what we want. And in fact, this works under GRH. So under GRH, there will be no problem, and this would be the end of proof. And it also works for almost all Q. So, so we don't know this for all Q, certainly, but if we exclude a certain number of q, let's say prime q, using zero density estimates, one can show that there's reasonable zero-free region for L functions modulo typical numbers q, and then using that and Perron's formula, one can get a bound on the character sum. So this is kind of the line of approach that we took with Kulmer and Manderel when we were looking at the exceptional set of primes q. So if you throw away some primes, you get some amount of cancellation in character sums, and then you can exploit that.
How did you get down to only boundedly many factors?
Yeah, there was firstly, one of our primes was less than q to the epsilon as well, which required us to use the Matomäki residue method because one of the primes is very small. And we had to work with the logarithmic version of the character sum. So then one can get some bounds using only sort of very weak bounds on the zero-free region.
But the bounded,
yeah, so
they're coming from that.
if you throw away a bounded number of characters, then you get that zero-free region of the form 1 minus c over log q, where c is as large as you want. And for logarithmic sums, that's enough, but not for the ordinary.
So you say under GRH this method works for E3.
Yeah, for E3. Yeah.
For E2 you said.
For E2, it doesn't work, but it would work for the problem where you are looking at the so you're throwing away a few bad A, so you're looking at almost all A modulo Q that you want to represent, and it would give you that if you throw away a power of log many bad residue classes, then all the rest you can represent as a product of 2 primes less than Q. Yeah, but it doesn't quite give the full statement under GRH for the 2 primes. Okay, so as I said, unfortunately, we don't have such bounds on character sums, but let me just say how little is really known about cancellation in character sums. So one could ask, can we get any bounds on these sums for arbitrary Q? And not really. So there's a couple of things. One thing is that if there's an exceptional quadratic character, then that completely biases the distribution of primes in quadratic residues versus quadratic non-residues. So there would be a bias in the sum, and it would not be small. But it's not only the exceptional character, also the other characters cause problems. You could take any other character, let's say a character of order 5. And so we have, for example, the following problem, which I don't know how to answer. So take a character of order 5, so it's taking values, integrals of unity of order 5, and show that the primes less than Q cover all the possible values of this character. So chi 5 of P takes all the possible 5 values within the primes less than Q. And this already I don't know how to show, which means if this doesn't hold, then there's no cancellation whatsoever in the character sum. So one can get some bounds on this problem. Elliott has some bounds on how big the primes need to be, but they're not quite strong enough to obtain this, for example. So this means that the direct Fourier approach runs into some serious trouble if you're looking at every modulus Q. Okay, so we have another approach, which is also natural, and this is going to work. So an additive combinatorics approach, which originates with the work of Ben Green on eigenvalue proportions of primes. So Green showed that if you're counting solutions to P1 plus P2 equals 2P3 into primes, in other words, you're looking for 3-term progressions in the primes, you can replace the primes by a model function, model set, which is a dead set. But it has all the same properties relating to this equation. So there's the same number of solutions within this dense set to this equation. And using that, he was able to prove the first non-trivial case of the Green-Tal theorem. So this approach can be generalized to other equations as well. In particular, Matomäki and Shaw and Matomäki, Maynard and Shaw considered the Goldbach equation. So P1 plus P2 plus P3 equals N using the transference principle that you transfer the primes to a dense set of the integers where you can analyze this problem. And so we want to follow a similar idea. So we wish to show that if you're looking at the count of solutions to P1, P2, P3, congruent to A mod Q, we can replace the primes by some dense set, hopefully of a relatively large density, such that the count is the same up to a normalization factor, which depends on the density of the primes. So if we could do this, then we could apply various tools from additive combinatorics to attack the problem. And so indeed we can do this. So we can process a transference principle. So to state the transference principle, let's just introduce two pieces of notation. So the multiplicative Fourier transform of a function g on z mod q star is just the sum of g twisted by chi as a character. And by gr, I denote the LR norm of a function g. Okay, so our multiplicative transference principle is the following. So this is closely modeled by the works of Green and Matomäki in the case of additive statements. So take any function f on 1 to q, non-negative. So think of this as the indicator of the primes. And suppose that we have two properties for this function. One is that there's a pseudo-random majorand for f, which means the function nu such that it has mean value 1, so this is a normalization condition. And the other is that the Fourier coefficients of nu are uniformly small. And the other condition left is that the LR norm of the Fourier transform satisfies this bound for some fixed R. And this is a natural bound because this would be, there could already be one character that contributes this much to the LR norm. So it kind of corresponds to a contribution of one possible character. Okay, so if you make these assumptions, then you can find a bounded function g, which is called the dense model. So this kind of corresponds, if g is an indicator of a set, then this would be the set where we're transferring to primes to, such that the count of solutions to our equation m1, n2, n3 is a mod q, with weight f is the same as the count with weight g, so which is dense model up to little errors. Okay, so we can transfer to this dense set. And secondly, in any coset of z mod q star of bounded index, f and g have the same mean value. So basically this g captures all the properties of f, such as what's the density of f on, let's say, quadratic residues.
Multiplicative cosets, so you're using, so we don't know what the structure of.
So things like kth powers or their cosets. Yeah, so that would be the kind of cosets that we're looking at. So the proof of this transference principle is quite similar to the additive one. So the main idea is to construct this G as a convolution of F with the indicator of a multiplicative Bohr set, which is the Bohr set corresponding to the characters where the Fourier transform of F is large. Okay, so one can show that this function is bounded and that F minus G is Fourier uniform, which means that when looking at this kind of count, we can just split F as G plus F minus G and throw away the contribution of F minus G. And we're left with just the contribution of G.
Wait, going back a few slides. In the work of Matomäki, why were they doing this additive combinatorics on the Goldbach problem? What were they trying to do? I guess
because they were doing short intervals. So they were doing the Goldbach problem in very short intervals.
Okay.
Yeah. There's also work of Shao where he looked at just the original Goldbach problem and gave a new proof of that using transference.
Results which went down before, I assume, using without additive combinatorial.
Yeah, exactly.
They also get an optimal density like he does for this
Yeah, so
relative version of the multiplicative.
you mean
He has
for the
this-
primes?
Yeah, Fernando has this 3/8 or something.
Yeah, we have 3/8, in fact, yeah. Yeah. So I'll tell about that just in a moment. Okay, so this is the transference principle. And so the thing we want to do is apply it to the indicator of the primes and check that all the conditions are valid. So let's do that. So F is now the indicator of the primes of the Q. And so as the majorant nu, we take an upper bound sieve for the primes. That's a natural one to take. Let's say we take the linear sieve. So nu is a truncated divisor sign, where the divisors go up to some number difficulty. And for this sum, we can compute its Fourier coefficients and so that they're small. So if we're computing the Fourier coefficient of nu at chi, just by inverting the order of summation, we get this expression. And now here we have a character sum over the integers. So we can apply the Burgess bound on such character sums. And the Burgess bound says that there's a lot of cancellation in the sum as long as the length of the sum is at least q to the 1/4 plus epsilon, if q is q-free. So this is where the q-freeness comes into play. So in the main theorem, I stated it was for q-free moduli. So that's exactly because of the Burgess bound. So one can also get results for non-q-free moduli, but then the Burgess bound is weaker. So
these new bounds of hetero and Young are only for L functions, right? Only for they don't apply.
yeah, that's right.
You need you need arbitrary interval.
Yeah, but we somehow actually overcome the problem of sort of the 1/3 versus 1/4 inverses, because it is known that if the order of the character is bounded, then we have the stronger version. So that's actually something useful for us. So it's not that much of a problem, but yeah.
But wait, here at least you only need the initial interval. So
Yeah.
you only need character sums for the initial interval, is that right?
Yes, I guess.
The other one's much
Yeah.
longer.
Yeah, that is true, yeah.
So I think that word does apply, it's just that it's
Too long.
Yeah, that's a good point, yeah. Okay, so as long as the length d of this divisor sum is less than q to the 1/3 minus epsilon, we get cancellation. And applying the sieve, it means that the mean value of this majorant is 8/3 times the mass of the primes. So it overestimates the primes by a factor of 8/3, which means that our dense model has density 3/8. So this is going to be important. And the other thing we need to check is that the LR now of the Fourier transform of F satisfies this bound. So I won't say much about it at this point, but it's just applying the Hallas-Montgomery method and the Burgess bound. So you look at the dual problem of this, and then you apply a majorant on F, so new majorant, and then you apply Burgess similarly as above to get this kind of thing.
Burgess for arbitrary intervals here, or is it also just?
This is also for the initial interval. Yeah. So we only need the initial interval version. Okay, so this means that we have the conditions for F that we need to check. So it means that we have transferred the problem to a set of density 3/8, where we are now counting solutions to A1, A2, A3 equals A for the Q. And so coming back to Q-free versus arbitrary moduli. So what if we were working with non-Q-free? Well, then the Burgess bound is weaker. It would give 1/3 minus epsilon for the density. And there's actually a kind of threshold at 1/3 because if you have a set of density 1/3 minus epsilon, you cannot expect the threefold product to cover everything, even if you know that A is well distributed in cosets. You need something more than that. So, so that's kind of problematic. But if you just look at slightly bigger primes, so primes bigger than q to the 1 plus epsilon, then the density increases a bit, and it becomes 1/3 plus epsilon. And that you can work with already because it's bigger than 1/3. So there's some hope that information about distribution of primes and cosets is going to help you. But okay, so this is the conclusion so far, that we can transfer to a set of density 3/8. Okay, so I can ask in general, if you have a dense set of the multiple group of residue classes, what can you say about the triple-fold subset? And okay, so there can be some obstructions. For example, A could be the set of all the quadratic residues, modulo Q. So that would be a density 1/2 set, but it would only cover half of the residue classes because it's a subgroup. Or similarly for cosets. But there is a theorem of Kneser, which is very helpful here. So kind of a generalization of the Cauchy-Davenport bound. But if you have any finite abelian group and you have two subsets, so I'm writing things in multiplicative notation, even though everything is abelian in this talk, because we have a multiplicative problem. So then the size of A times B is at least the size of A plus the size of B minus the size of the stabilizer of A times B. So the stabilizer is a set of elements which fix this set. Sorry, this would be AB. A times AB equals AB. Okay, so this is Kneser theorem. And so if we know something about the set A times B not being trapped into cosets of small index, then this gives us good bounds on the size of the product set. So in particular, in our setup, the set A has density 3/8 minus epsilon. And so now if the size of the stabilizer is a bit less than phi of q over 8, let's say phi of q over 9, then the size of A times A is at least twice 3/8 minus the size of H, which is bigger than 5/8. And the point is that if the size of A times A is bigger than 5/8 phi of q, then because A itself had size 3/8 phi of q, these two sets are going to intersect. So A times A and A inverse G are going to intersect for any G, which means that A times A covers everything. So what we just want to guarantee is that A times A has density at least 5/8. And so if the size of the stabilizer is small, we can do it. So we can assume that the stabilizer is bigger than 5 q over 9. And the size of the stabilizer is phi of q over k for the number k, where k is the index of the corresponding subgroup. So if the size is bigger than phi of q over 9, then the stabilizer is as index less than 8. And this means that the set A times A must be equal to the union of cosets of some subgroup of index less than or equal to 8. So for example, A could be the union of, let's say, two cosets of the 5th power residues. So this would be one possibility here. So it's some union of cosets of index less than 8. Okay, so we need a bit more information on A, but this is what we know so far. So it's a union of cosets of index less than 8. So another thing we can show using the transference. So basically, all the properties of the primes are transferred to the set A. So we already showed that it has the same density in cosets. Also, A times A has the same density as the product of two primes. So one can show that products of at most two primes cover every coset. And this means that, sorry, this would be union. Either A or A times A intersects any coset. So A union A times A intersects every coset. So this is something we can also use. And so we can assume that A times A doesn't cover everything, because otherwise we're good. And now we put all of these things together and do a little bit of elementary group theory to see what kind of conclusion we can draw about the set A. Okay, so if A has all the properties above, so it has density 3/8 minus epsilon, it's A times A is a union of cosets of index less than 8, and A union A times A intersects each of these cosets. Then one can conclude that firstly, the index of the coset must be 3k plus 2 for some k from 0 to 2. So it's either index 2, 5, or 8. Also, A itself must be contained in the union of exactly k plus 1 cosets. And A times A must be equal to the union of 2k plus 1 cosets. And finally, we know what these cosets are. So for A, it must be in a union of k plus 1 consecutive cosets if you go along the circle. So these are the kind of obstructions, and indeed these we have to rule out. So if A was such a set, so the union of these cosets, it would not cover everything. There will be one coset that will be left over from the free product.
How do you know it's sort of this middle third interval?
You need to do a bit of group theory. It's not obvious that it has to be that, but yeah, you can check. I mean, in principle, you could do it by hand even, because everything is of index less than 8. So there's only a bounded number of possible cosets you could look at. So one could do a brute first, but one could do it with group theory as well. Okay, so as an example, as I already said, A could be contained in the union of two cosets of the 5th power residues. So let's say g squared and g cubed. So if this was the case, then A times A would be contained in 1g4, and the triple product would contain everything except the coset 1, so the subgroup itself. And that would be a problem. So A times A like A would not cover everything. So this we have to rule out somehow. And again, we transfer back to the primes and try to show that the primes cannot be trapped in this way. It's just a union of cosets. Okay, so this is just the example we had before. And it leads to a model problem about the primes, which is now easier than the model problem we had for in the direct Fourier approach. So take a character of order 5, modulo Q, and take a 5th root of unity. Can you show that there's a prime less than Q such that along these primes less than Q, the character is not trapped into just two values of this, two of the 5 roots of unity, namely zeta and zeta cubed. And this likely we can show. So it's based on an that Szabo used in his work, which comes from work of Heath Brown when he was working on the Linux problem. So there's this kind of inequality for character sums, weighted logarithmically, and with an additional weight function, that the real part of a character sum with a weight is never too large. And the 1/8 here is important, so that comes from Burgess. And okay, so using this, one can show that indeed it cannot be the case that chi of p is trapped into just two of these cosets, because one can then have by taking a suitable character of order 5, one can ensure that real part of chi of p is always quite large and positive, whereas this is saying that it's rather negative, sort of more of the time. And one can do a similar argument for 8 powers. So if there was an 8 power character such that the primes were trapped in 3 cosets of that character, one could again get a contradiction from this inequality. Okay, so there's still the case of quadratic residues. So that I'll return to later. It actually causes some extra trouble, but at least the 5th power residues and the 8th power residues are handled by this kind of arguments. Okay, so this was our conclusion from transference. And now there's a couple of, so this was kind of the main argument, but there's a couple of additional complications we need to handle. One is that, so we not only need the triple product to cover everything, we need a lower bound for the number of representations. So not only that there's, let's say, one representation, because actually this approximation is only up to little or errors. So you need there to be many representations in this form to get some information about the primes. So luckily this can be handled because there's a popular sums version of Kneser theorem due to Grunkiewicz. So this gives you lower bounds on the triple convolution if you know bounds on the sort of essential product set, where you're throwing away small sets from the original set and you take the triple product. Okay, so the other thing is that so we know that the model set A and the set of primes have the same density on cosets, but only up to little or 1, which means that in order to show that A is not trapped in a coset, we actually need to show that there's a positive proportion of primes that are not trapped in those cosets. And so it means we need quantitative bounds for primes and cosets. And therefore we need to revisit the problem we had previously about primes and cosets. And so now let's ask, so if we again have a character of order 5, can we show that there's a positive proportion of primes up to q such that the character is not trapped into 2 values, zeta squared, zeta cubed? And unfortunately, I don't know how to show this. What the argument of Zaber and Heath-Brown gives is lower bounds on the logarithmic measure of this set. So if you're looking at this set of primes which are outside these 2 cosets, the logarithmic measure is large in some scale. So we have to do with this weaker version that we can only pass to a certain, possibly quite a small scale where we have the density of these primes outside the 2 cosets. And so this leads us to rerun the same arguments, but now with a logarithmic weight. So now let's look at products of 3 primes, where the 3rd prime is of size q to the alpha, where alpha is such that we know a good bound at scale alpha for the number of primes outside these 2 cosets. And let's add a weight of 1 over p on this, just to match this weight here. Okay, and we run the same argument through, but it's slightly trickier because now we have one of the primes being small. So how can we handle that? So we want to now replace the count of P1, P2, P3 in a progression by transferring the first two primes, so the large primes, into a dense set. But the third prime we just keep as it is. Because for that, transference would not be very useful because the sum is too short to use purges, so we don't get bounds onto the density of these primes. But actually in the argument previously, we only basically needed to look at the twofold product set. So we just needed the twofold product set to be bigger than 5/8. And then even if these remaining primes are small, one can just use them to show that we're not trapped in a coset. So that's the only extra information we need from the third prime. Okay, so the proof of this is similar as before. So we use a dense model on the two primes, large ones, but on the third one, we need an LR bound. So we need to understand the Fourier transform of the short character sum of the primes to some power R. So in the case alpha equals 1, we already did this, but now alpha is something small, like 1/1000, and we need a restriction estimate for this character sum. So this can still be done because, so one way to prove this kind of LR estimates is to interpret this as a large values estimate. So we want to bound how often the character sum is bigger than delta for any delta, which the bound is by, it's just delta to the minus R. If you have such a bound, then you can just sum diagonally over different delta. And okay, so we cannot directly apply Burgers because this sum is very short. But what we can do is raise the exponential sum to a large power to make its length approximately Q. So take a large power of this, so it's of length approximately Q, and then that gives you a new character sum of length about Q, for which one can apply large values estimates. So the Haas-Montgomery method, similarly as before. So by raising to a suitable power, we can make the sum long, and because there's logarithmic weight, it's still a dense set. So everything works as before. Okay, so this handles the problem of not knowing that there's a positive proportion of primes in a coset, because we could pass through this scale, Q to the alpha, where we did have a positive proportion, and work with that scale, and then use large values estimates on the short character sums. Now the one, yeah.
Use a dense model for LR for R is 1/alpha, like something like that. Or am I
yeah, I guess no, R is something close to 2 actually. Yeah, R is approximately
I thought you
2.
wanted to take a large power of this sum underneath that you get.
Yeah,
large
R is
power.
bigger than 2, you can say so.
Yeah.
Not large. I also was thinking R is 1/.
Yeah, I think R here is something close to 2. Because that's.
But then I don't understand the bottom. You say, okay, maybe I'm missing.
So I think he wants to deduce the result with R a little bit bigger than 2, but to prove that result, he's doing this large values estimate where he's estimating the value with a very large power, which is a different constant that is large and does look like 1/alpha, but it's a different constant to R.
Yeah, yeah, exactly. Yeah. Okay, so there's one remaining obstacle, which is the case of quadratic residues. So we handled the 5th powers fine and the 8th powers using this passing to a smaller scale, but we still need to handle the quadratic residues. And something slightly different happens here, because so if we could show that for a quadratic character, if you look at how many primes are in a coset, the logarithmic measure is positive, then everything would work similarly, just as before, like for the fifth power residues. So this we can show just quite similarly for the quadratic non-residues. So we can show that there's a lot of primes of the Q that are quadratic non-residues. But for the quadratic residues, actually, it's problematic. So we cannot quite show this for the quadratic residues. And so we have to resort to a slightly weaker statement. Namely, what we can show is that if we don't have a good bound on quadratic residue primes, we still do have a bound which involves L1 chi, so the value of the L function at 1 times this kind of Euler product. So the proof of this bound is related to recent work of Dunn, Kerr, Sparlinski, and Zaharescu. So basically the problem of bounding how many quadratic residue primes there are up to Q.
L1 chi can be very small.
Yeah, it can be small, yeah. And that is the problem. So if L1 chi was large, then this would be good. But if it's small, then that's a problem. But luckily, if we are in this scenario, then actually this lower bound, even though it looks weak, it is the correct lower bound. So if you have an exceptional character, then this is what we expect the sum to be. And therefore, we can also get upper bounds of the corresponding order of magnitude. And this means that we can construct a majorand for the primes, which takes into account this factor. So the primes kind of see this drop in density. And you can use a majorand which takes this into account. And therefore, we sort of work relative to this density, which has now dropped. And we can still prove similar things like the LR estimate.
I mean, you do need to know it's not too small. So
Yeah, we need the Siegel bound for Q to the minus epsilon.
so you in effect,
I guess Q to the minus 1/2 would suffice. Yeah, I think we only need the Q to the minus 1/2. I think, but I haven't checked.
so not Ziegel.
Yeah.
You need Ziegel or not?
Okay, we use Siegel. Perhaps we need Siegel after all.
I mean, I understand it's relative, but you would imagine that if it's as small as
Yeah, of course. It
to the minus
would be a
1/2, it
problem.
would
So
sound.
if L1 chi was 0, that would certainly.
Yeah, I agree with you. But maybe Q to the minus 1/2 is already too small.
Yeah, so we use the Q to the minus epsilon bound of Siegel.
Okay, that's Ziegel.
So this allows us to, because we can construct a majorand which sees this density, we can run through the same argument. And it's not a problem that we have the density is smaller than it was previously, because it just needs to match the density of the majorand. And that's the conclusion of the proof. Finally, let me briefly mention a couple of related results we obtained also. So one can ask, what about all Q? So if you don't restrict to Q3 moduli. And as I already kind of indicated before, if you increase the primes a little bit to Q to the 1 plus epsilon, then you can still do it. Because the key thing was that the dense model had to have density bigger than 1/3 to be able to say something. So this bound we can still get. And also we look at the problem of what can we say about E2 of Q? So it's relatively tricky to say good bounds on this. For example, we don't know that E2 of Q covers almost everything for arbitrary moduli. But what we can show is that E2 of Q covers at least 2/3 minus epsilon proportion of all the residue classes. So again, this is tricky because if the primes were trapped in some union of cosets, then you would not cover everything. And this improves on an earlier estimate of 3/8 for the density by Zabel.
But if Q minus 1 has few prime factors.
Yeah, that helps.
And then,
Yeah, because then we don't have these cosets.
And then you probably
Yeah,
can
they don't exist. Yeah, yeah. So that helps a lot. That's a good point. If Q minus 1 has no small prime factors, that helps. Okay. Finally, oh yeah, and this proof also uses all the same techniques, and in addition, the multiplicative energy of the primes plays a role, because you can lower bound this density of products of 2 primes by Cauchy-Schwarz, and there you get the additive energy of the set of products of primes comes into play. So finally, let me mention something that we very recently started working on with Kaisa Matomäki and Joni Merikoski. So this is something that's very much ongoing still, but we are looking at how to apply this kind of machinery, so the multiplicative transference principle, to Linux program. The problem about bounding these prime and residue classes. And the point is that the method I just described to you gives us lower bounds for products of 3 primes in arithmetic versions in a large range of these scales. So, for example, if alpha 1, alpha 2, alpha 3 are all equal to 1, then we have some bounds. And similarly, you can make alpha 1, alpha 2, alpha 3 bigger and get better bounds. So we can get some explicit bounds on the number of products of 3 primes in progressions. And this is exactly the kind of type 2 information that one needs when looking at the Linux problem using harm and sieve. So if one applies harm and sieve to the set of primes up to Q to L in a congruence class, one ends up with the need of getting good bounds on this kind of type 2 sums. And so our bounds are lower bounds, which is a bit unusual in harm and sieve, but that's still okay as long as the exponent that we're looking for is large enough. We can throw away a lot of stuff, and harm and sieve can do with just lower bounds on this kind of sums. So we believe that we can use this to give an L function free proof of Linux theorem with some reasonable value for the exponent.
Right. What is the aim there? To improve the exponent or to give an L function free proof?
The aim would be to improve on the exponent, but
yeah,
we still have a lot of work to check what actually is the kind of exponent that we get here.
I don't know what
So at the moment we don't know.
free proof means. You're using L functions everywhere.
Not really. I mean here, like one can replace this, use Brun-Titchmarsh and the versus bound, which can be proved without L functions and things like that.
But the aim is to improve the exponent. What is the world record?
L equals 5 by auxiliaries. But so it's not clear yet what exponent we will get out of this. I think that's all I want to say. Thanks for listening.
Any questions for Joni? Please.
So for the quadratic character, you're building this into your major and your transference.
Yeah, that's right.
And so you explicitly use.
Yeah, we take into account the density.
Could you do the same thing for the other low index subgroups? So you're directly proving that you have a result for the quintic character.
Yeah.
For example, could you have an alternative argument that's much more in keeping with your quadratic character thing, where you're putting the quintic character in your major based on whether there is a bias or not, and you don't need to know? Yeah,
that's a good idea. Yeah, I guess I could try that. I guess one thing is that so in this kind of estimate, for example, for the quadratic character, there's some explicit constant hiding here, and Yeah, I'm not sure what the explicit constant will be like. So that might influence the effectiveness of such a transference. Yeah, but one could try that experiment.
In that vein, the transference is effective, I'm sure, but the Landau's equals 0 is not. So that would be good to sort out whether you're using that seriously or not, because it doesn't sound like it should hurt you.
Yeah, yeah, we don't use it very seriously.
In other words, your theorem may be at this point that, or you don't know when it kicks in.
Yeah, we kind of avoid the Landau's equals 0 because it's okay for us if there's even just a few quadratic residue primes, we can still.
Yeah, it sounds like you should get around it, just
Yeah.
like in the original Goldbach, I think
Yeah.
you also had that problem.
Yeah, I think that sounds reasonable.
But just philosophically, it would be nice to know.
Yeah. That's a good question.
So you mentioned one of the reasons why you need to go to cube 3 q's is because the difference between this 1/3 and 3/8, and the 1/3 is like this cutoff.
Yeah.
And I was just wondering if you do products of 4 primes instead of 3 primes, you still get the 1/3, and then is it good enough to get it for all q?
Yeah, so products of
slide 10.
yeah.
So.
Yeah, so products of 4 primes are easier. Like initially, like when we were working on this, we got the result for 4 primes. So there one is much less machinery. So there's fewer obstructions for that you need to rule out about being trapped in cosets. So in particular, yeah, for 4 primes, we could do just primes of the Q for any Q, whether it's Q3 or not.
And it's also a new result, right?
Yeah.
Right. Any other questions? If not, let's thank you again. Thank you.